Okay, hi everybody. Welcome to session 1 of Vectorworks Marionette Monday. I'm Robert Anderson, Vice President of Integrated Practice for Vectorworks Incorporated. I'm here with Sarah Barrett, a member of my team and one of our outstanding Vectorworks evangelists. We're really excited to be bringing to Vectorworks users and to fans of algorithmic design an important new platform for you to realize your design visions, one that we call Marionette. As many of you know, generative design is a design method where sets of rules or algorithms, usually in the form of a computer program, generate part or all of a design. We've seen some fantastic examples of such algorithmic design over the past few years, and Marionette unlocks the potential of algorithmic design for Vectorworks users. But algorithms that are based on programming languages are kind of difficult to learn, to use, and especially to decipher. They lack the immediate results and malleability needed for the design process. So Marionette employs a familiar and easy-to-use flowchart metaphor to allow you to assemble useful programs using wires to direct the flow of data and create your design. Most importantly, these programs are easy to understand and easy to modify by people who don't have a programming background. We designed Marionette to be fully integrated with Vectorworks' complete range of CAD and BIM capability. This means that not only can you use it to create organic designs, but to prototype custom parametric objects and to automate other design processes. Over the next few sessions, we'll lead you through an in-depth training that will expose you to the full range of Marionette's capabilities, but really, your imagination is the only limit. With all that lead in, I'd like to introduce you to a valued member of my integrated practice staff, Sarah Barrett, who will be your Marionette trainer. Sarah has a background both in architecture and in algorithmic design, and she's going to be our guide to all things Marionette. Now, without further ado, please join me in welcoming Sarah as we change over.
Thank you, Robert, and welcome again, everyone, to our first Marionette Monday webinar. Marionette is the new graphical scripting interface for Vectorworks. Vectorworks has had scripting capabilities for a long time, but as Robert said, code-based scripting can be difficult to learn and implement, and hard for non-programmers and visual learners to use intuitively. Marionette makes scripting much easier to use, but to get started with Marionette, it is still useful to understand some basic rules of coding and scripting, mainly, what is an algorithm and how is one created? Algorithm is defined by the Merriam-Webster Dictionary as a step-by-step procedure for solving a problem or accomplishing some end, especially by a computer. An example of algorithms in everyday life might be assembly instructions for a piece of furniture or appliance, or another example might be a recipe for making cookies. Every algorithm needs two things: data and operations. Data, or parameters, are the pieces of information you start with. Operations are the actions you take or the commands you apply to your data. In mathematical terms, data are your variables and operations are your functions. In our assembly instructions, we have information on what tools and parts are needed to complete the assembly, as well as how to put them together. We have our data and our operations. Or in a recipe, the data would be ingredients and their amounts, and the operations would be the instructions for combining those ingredients. With Marionette, you can create algorithms using nodes from its node library. Nodes are the individual pieces, each datum or operation, that make up a script. This library of nodes can be found by clicking on the Marionette tool in the basic toolset. When you click on the tool, you see a drop-down menu in the toolbar as well as two modes, insertion mode and debug mode. To access the Marionette nodes, insertion mode must be highlighted. We will get to debug mode later in the webinar series. When you click on the drop-down menu, the resource selector appears. In the file browser pane on the left, there is a list of node file folders. If you click on a file, a list of nodes will appear in the viewer pane in the center of the resource selector. If you already know the name of the node you are looking for, you can type it into the search box at the top of the resource selector. You can not only search by name, but also by tag, As you can see in the preview pane on the right, nodes are tagged by folder. To select and place a node, double-click on the node you want, then click once in the drawing space. Like other plugin objects in Vectorworks, the tool remains selected, so clicking again in the drawing space will place another node. To help us understand how Marionette nodes work, we can start with identifying its different parts. Most nodes have both input ports and output ports. The input port is a white circle on the left side of the node where information is applied. An output port is a white circle on the right side of the node where data can flow from one node to the next. Each input port has a name that helps identify the type of data to be applied to the node, and each output port has a name that helps identify the type of data that will be supplied by the node. In this case, the two input ports are centerpoint and radius. This tells us that one input will be a 2D point that will be used as the center point of the circle, and the other will be a number that will be used as the circle's radius. The output port is a circle, which means the output will be geometry in the shape of a circle. These purple nodes with no input port are called input nodes because they are used to supply the data that starts a definition. Although there is no input port on the outside of the node, data can still be applied to the node by typing it into the object info palette. In the OIP, you will see boxes where data can be typed in. To build a network, we have to connect the nodes together. The connection between two nodes is called a wire. It is what allows information to flow from one node to the next. To create a wire, first select the node. Then, click on the output port of the node when the arrow appears, move the cursor to the input port of the next node, and click again. The nodes are now connected, and even if you move the nodes, the wires remain attached. A series of connected nodes makes up a network. It does not matter how many nodes there are. As long as it can perform a function, it's a network. It can also be called a script or a definition. This is Marionette's interpretation of an algorithm. If we want to see how a familiar algorithm would look as a Marionette network, let's go back to our recipe for Grandma's cookies. We know that this recipe creates one batch of cookies, and if we think in these terms, that every ingredient and instruction is based on making one batch, we can build an algorithm for any number of batches we want. Below the recipe, I have added some simple measurement conversions that we would need. As you can see, we need several nodes to accurately describe each ingredient in the recipe in terms of the number of batches. It is set up this way so that if we change the number of batches, all of the ingredients would be automatically updated. Not only do we have to put the ingredients in terms of batch number, but we also have to convert all the different measurements to one single type. Just as if you were putting dimensions on a floor plan, you would always use the same unit. For the second part of the recipe, the mixing instructions, our Marionette network would look something like this. Each action must be spelled out as if you were telling a computer how to make the recipe. You would have to tell it how to break and beat an egg and exactly how and where to combine ingredients. There is a limit to this though, and that is where the specific nodes come in. Every node has a script inside with a predefined command, and this is why it is important to know what each node can do. We will get to that in a minute, but first, a little more about the basics of a Marionette network. Information always flows from left to right within a node, and as long as wires are connected in the right order, it doesn't matter where the nodes are placed in relation to each other. This network works the same as this network. The second network is easy for us to read, so I would recommend keeping your nodes flowing from left to right across the screen in the order that they are connected. And if you're a perfectionist like me, you might get caught up trying to align your network perfectly. It can be very satisfying, yet it is a huge waste of time. I don't recommend it, although I understand that it can be hard to resist. Another important aspect of Marionette is naming. Naming comes into play in several ways when using Marionette. We are going to start with naming nodes for your own reference. When you select a node and go to the Object Info palette, you see that there is a box where a name can be typed in. Every node can be given a name to help you remember what that node is used for in the network. This is especially useful when sharing your network with others. In this network, we might want to name the input nodes to remind us what they are being used for. We could name the point 2 node Circle Center Point. And the real node Circle Radius. As you can see, the names we gave the nodes are now in large print on the outside of the node, and the node type is in a smaller font below the name. The word we use to implement a network is run. If we want to see what a network can do, we have to run it. To run a network, you simply right-click on any of the nodes and select Run Marionette Script. You can also run a network by selecting a node and then clicking the Run button in the OIP. The result of the network appears at the coordinate specified. The result is always selected when it is first created, so if it is not visible after the network is run, you can click on the Fit to Objects button in the menu bar to view it. As you can see in the OIP, the geometry is created as a group and it is named. All resulting geometry is named as Marionette Group and then something more specific to connect that object back to the network. In this case, it is named Marionette Group Circle, then underscore, then a number. The number is not important to us. It is only an internal identifier for Vectorworks. If we double-click on the group, we see that it only contains the circle we created. If we want to change some part of our network and run it again, the new geometry will replace the old geometry. You see that it has the same name as last time. If we want to disconnect our geometry from the network, we can either ungroup it or change its group name. If we do this and run our network again, new geometry will appear without overriding the old geometry. In order to fully utilize the myriad of nodes that are in Marionette's node library, it is helpful to understand what nodes exist and how you can find the nodes you're looking for. As we mentioned before, algorithms have two types of information, data and operations. Marionette nodes likewise can be separated into two different types, data and objects. Each of these types can then be separated into two more categories. Data can be separated into data creation and data manipulation, or nodes that change or alter data, and objects can be separated into object creation and object manipulation. If we look at this network that creates a series of polygons, we can classify the nodes in this network into these four categories we just mentioned. In this network, the categories can be shown in a specific order, but this is not always so. The more complex a network, the more likely these four types of nodes will become intermixed, but they will always work together in the same ways. So let's see what type of nodes fit into each category. One way to figure out what a node does is to look at its color. This is a bit of an oversimplification of the color system, but is a good place to start. As you can see, purple nodes most often deal with data creation or collection, and nodes that range from brown to gray tend to deal with data manipulation. Blue and green nodes deal with specific objects and their creation, while pink nodes deal solely with object manipulation. Within the Marionette node library, data creation nodes can be divided into 3 categories. These are input nodes, get nodes, and object info nodes. Input nodes are the nodes that begin a definition. Data must be entered in the OIP of the node. These nodes supply the basic criteria of every definition, and once the definition is complete, these are the nodes you will use to alter the definition, to change the variables. Input nodes have their own separate folder. They are located here in the node library. Nodes that begin with the word get are used to extract data from existing objects. Get nodes always have an input for an object, sometimes a specific type of object like a 2D polygon or a NURBS object. This is why get nodes are often located in their relevant object folders. As you can see, these nodes are all different colors because they are used to extract data from different types of objects, or in the case of the get opacity node, it is a part of a separate yellow category that only deals with attributes. Almost all nodes in the object info folder are get nodes. The reason they are in their own separate folder from the other get nodes is because they can be used with multiple types of objects. The object info nodes are located here in the node library. Data manipulation nodes are nodes that change data. 2 examples of data manipulation nodes are data flow nodes and math nodes. Data flow nodes only have inputs that receive data and outputs that supply data. These are the nodes that make sequencing and repetition possible in Marionette. They are located here. Math nodes serve a similar function to data flow nodes, except that they deal specifically with mathematical functions. The math nodes are located here in the library. Object creation nodes are in the different object node subfolders depending on the type of object they create. An object creation node always has the object type as its name. The input ports of object creation nodes receive data, and the output ports supply an object. The 4th type of node, the object manipulation nodes, can be divided into 3 categories. Action nodes are nodes that have a name that starts with a verb, other than get or set, and these nodes manipulate objects. Action nodes that only apply to specific types of objects will be found in that object node folder. Nodes that begin with the word set are used to apply new data to existing objects. Set nodes always have an input for an object as well as an input for data. Set nodes are often located in their relevant node folders. Set nodes that deal with multiple types of objects can be found in the object info folder in the node library. Nodes in the operations folder are all action nodes. The reason they are in a separate folder from the other object manipulation nodes is because they can be used with multiple types of objects. They can be found here in the library. If we go back to the network where we classified the nodes, we can see how they work together. The data creation nodes in our network are all input nodes. Some of the data they supply is then changed by the data manipulation nodes. There are 2 data flow nodes and 1 point node. We've not mentioned point nodes before, but they are an important type of data manipulation node. They specifically deal with points, which are not quite objects. The object version of a point is a locus, and there is a separate folder for loci in the object nodes list. The data from these nodes is then applied to an object creation node, specifically a node that creates a regular polygon. And then this polygon, or in fact a series of polygons, is then manipulated by a move node. Now that we have seen examples of how the different types of nodes work together, we can try building our own network. We are going to try to build this network from scratch. This network creates a grid of loci inside an existing polygon. A network like this could be applied to a more practical purpose, like creating a column grid on a floor plan, for example. If we look at this network, we see that it starts with a name node, an input node that allows you to reference existing geometry in your Marionette network. So we know that before we start building our Marionette definition, we must first create some starting geometry. So let's draw our own polyline. Once we have our polyline, we need to give it a name in order to connect it to a network. In Vectorworks 2017, an object can be named by typing in a name in the box at the bottom of the OIP in the Shape tab. In prior versions of Vectorworks, this box was under the Data tab. Since we are going to be using this name again, we can copy it by highlighting it and typing Command-C on a Mac or Control-C on a PC. Next, we need to get a name node. The name node can be found in the input folder in the file browser pane. Now we place the name node in the drawing, type X to exit out of the Marionette tool, and paste the name of the polyline into the box labeled Name in the OIP by typing Command or Control-V. Next, we want to uncheck the box labeled Create Duplicate Object. This box should be left checked if the Marionette network will change or delete the geometry in some way, but since we are only referencing the geometry, it's not necessary. Now that we have referenced our geometry, we need to get its location in the form of coordinates. Let's go to the Object Info folder and find the Get Bounding Box node. As we mentioned earlier, nodes with get in the title are used to extract data from an object. Get Bounding Box will give us the top left coordinate and the bottom right coordinate of a rectangle that fits around the object. Now let's connect the Name node to the Get Bounding Box node. The top output port is the top left coordinate and the bottom output port is the bottom right coordinate. The top left coordinate will give us the minimum x value and the maximum y value, while the bottom right coordinate will give us the maximum x value and the minimum y value. We want to create a list of values between the min and max x and the min and max y. So first we need to separate those x and y values from each other. To do that, we will get some xy nodes from the points folder. We need one get xy node for each of the Get Bounding Box output ports. Now we have separate outputs for the two x values and two y values. Next, we need two range nodes. The range node is a very useful node that is great for creating a sequence of numbers. Whenever you want to find out more about a node, you can click on Description in the OIP. The range node creates a series of numbers between start and stop. There are three inputs: the starting number, the ending number, and the number of steps between start and stop. The first range node will be for the x values, and the second for the y values. So let's connect the top left x, the minimum x, to the start input, and the bottom right x to the stop input. Next, we will go to the second range node, and we will connect the bottom right y, the minimum y, to the start input, and the top left y to the stop input. Now we need the number of steps in the range. Let's go to the Inputs folder and get an integer node. An integer is a whole number, and in Marionette it is used for counting and numbering as opposed to measuring size or distance. Since we want the same number of steps for both the x and y range, we only need one integer node, and we connect it to both our range nodes. Let's take this opportunity to name a few of our nodes, just for our own reference. First, we can name our integer node number of grid spaces, and also give it a value. And then we can name our different range nodes x range, and y range. Now we need to combine our two ranges. Whenever you want to compare or combine two lists, you will probably want to use a mix2 node, which can be found in the data flow folder. This is a very powerful node that allows you to mix and match two lists in 4 different ways. With the mix2 node, we can create lists of the same length based on the shorter list by cutting off the length of the longer one. We can create lists of the same length by repeating the last value of the shorter one until it matches the longer one. We can create lists of the same length by cycling through the values of the shorter one until it matches the longer one. Or we can cross-reference all the values. This is done by repeating every value of the first list the length of the second, and cycling through the second list the length of the first. The result is 2 lists that have the number of values that is the length of the first times the length of the second list. When you match these 2 lists together, you see that there is every possible pairing of values between the 2 lists. Let's go back to our network. We want every possible combination between our x and y values, so let's go to the OIP of the mix2 node and choose cross-reference. Whenever I use a mix2 node, I'd like to name it based on the list matching I choose, so let's name this node cross-reference. Now we need to make points from our list of x and y values. So we will need a point2D node from the point section. This will combine our list of x and y values back into a series of xy coordinates. Now we have a network that creates a list of 2D points that overlay our polygon in a grid. If we want to see these points, we need to create a locus for each point. So let's go to the drop-down menu and get a locus node. You can find it in the locus subfolder within the objects folder. Remember too, that if you know the name or the section of your node, you can always type that into the search box at the top of the resource selector. So let's attach the locus node and then run our network. As you can see, we have an array of loci, but the grid outline is in the shape of the poly's bounding box, not the poly itself. We need to add a condition to our network that removes the points from our grid that are outside the polyline. If we go to the folders Objects, Poly, and then 2D, we will see a node called Is In or On Poly. This is a node that takes an input of a polyline or a polygon and an input of 1 or more points. It returns a true or false value for whether each of those points is inside that poly. It also has a separate output that returns the points that are inside the poly. So now we can detach the locus node from the network, then attach those 2D points to the is-in or on poly node, as well as attach the name node to the poly input. We can then reattach the locus node to the point output of the is-in or on poly node. When we run the network again, we see that only the loci with points that are inside the poly are drawn. Now that we have this network, we can start to make changes if we want. We could change the number of grid spaces and then run the network again. Or we could change the shape of the poly. And then run the network again. The design possibilities can really open up once you start using Marionette. Do we have any questions? Is there a library shortcut? Yes, there is a way to search the node library. Instead of clicking on a particular folder and selecting a node, you can type in the name of the folder into the search box at the top of the resource selector. Also, if you already know the name of the node you are looking for, you can type that name into the search box. Can you use the Align Distribute tool to organize nodes? You can to a certain extent, but the wires that extend from the outputs of nodes are included in the node's bounding box, so aligning and distributing connected nodes can get tricky. Aligning left is never a problem, but other alignment options can be. Is Marionette specific to Vectorworks Architect? No, it's not. Marionette is available to Landmark and Spotlight users as well as Fundamentals users. I believe Marionette can be highly beneficial to many types of designers because it is a tool that helps automate processes, and these can be any process, from creating geometry to laying out a light plot to creating a database. What version of Vectorworks has Marionette? Marionette is available in Vectorworks 2016 and Vectorworks 2017. The version of Vectorworks that I am using in this webinar is 2017. Can you turn a network into a script, and can you place it in a script palette? There is a way to turn a network into a script. It's very simple. You right-click on any node in the network, and you select Save Marionette Script as Python script. And you get a dialog box that prompts you to save your script as a PY file. Once you do that, you can load that script into a script palette just like you would a traditional script. How do you know the kind of input to apply to the node? Well, there are a couple of different ways to figure out what types of inputs are appropriate for each node. If you look at a common node like the rectangle node, there are 4 inputs. The names of the inputs try not only to describe the type of input, but also the purpose of the input. For example, origin refers to the bottom left point of the rectangle. The name of the input could have been point because that is the type of input that the port takes, but that would not tell the user which point on the rectangle. Bottom left point would be too long, so origin is used. Since the input port names are only one word and often abbreviated, it can still be unclear. To learn more about the node, you can click on the Description button in the OIP. In the Description dialog box, there is a brief explanation of the node as well as descriptions of the different ports. If you are still unsure as to what type of input to use after you read the description, you can click on Edit, and this opens up the script editor that shows the Python code inside the node. If you look at the line that says point equals marionette.portin, and then parentheses, what is inside the parentheses is the default value of the port, and then a comma, and then the name of the port. Parenthesis 0, comma 0 parenthesis is the proper way to write an xy coordinate with an x value of 0 and a y value of 0. So from taking a peek at the script inside the node, you can get some more information about the node. If you look at the other marionette.portin lines, you can see that the default value for width and height is 1, meaning that those input ports take a number. We know that the width and height of a rectangle is a distance, so then the input node we would use would be either a real node or a dim or dimensions node. The fourth marionette.portin line is for orientation. You can see that the default value is the xy coordinate 1, 0. In this case, this 2D coordinate represents a rotation vector. The vector 1, 0 is equivalent to a rotation of 0 degrees. When using the rectangle node, I think of the orientation input as optional. If I don't connect a node to that input, the default value will be used, meaning the rectangle will not be rotated. You're welcome to use this input to rotate your rectangle, but if you're not comfortable using vector rotation, you can always attach the output of the rectangle node to a rotate node and give it a rotation that way. So that's all we have for our first Marionette Monday webinar. If we did not answer your question during the webinar, there'll be a list of FAQs posted on the forum at forum.vectorworks.net. Join us next time for part 2 of our Marionette Monday series. Thanks!